I have two differential equations up here. The top one is from page 69. It's problem number 10. And this is one we're going to end up working. It's called a first order linear differential equation with linear coefficients. And so these two terms are linear expressions. Alright, now, but look at this one right here. This equation, how is it different? It's missing these two constants. And what we have here, when you think about it, is an equation with homogeneous coefficients. Because 3x and 2y, 2x and 7y are all order 1. And so when you have the same order in all those coefficients, then, or the same degree, then it's a homogeneous coefficient situation. And to solve this problem, we would use that technique where we let u equal to y over x, or we could let u equal to x over y. But it will turn it in, this substitution will turn this into a separable equation. Alright, well, this technique won't work up here because although these terms are degree 1, the constants are degree 0. And so they're not homogeneous coefficients. So, but the secret is to make an adjustment to this problem so that it ends up being this problem. In other words, how can I let those constants be 0 legitimately? Okay, it's a pretty clever idea here, what we're going to do. It ends up being a geometric translation, creating a new coordinate system. And, well, let's see how that works. So, I'm going to pull out these linear coefficients. 3x minus 2y plus 4, and I'll set them equal to 0. 2x plus 7y minus 1 equal to 0. It doesn't matter whether I use this negative sign or not because it equals to 0. I could eliminate the negative if I wanted to. Alright, now if you think about these, both of these are lines. And I'm not going to attempt to draw them accurately. I'm just going to pretend these are the two lines. And they're not parallel. If they had the same coefficients for x and y together, then they would be parallel lines, or they could be actually the same line. But they're definitely not parallel lines, which means that they're going to intersect somewhere out here. So here's the secret. In the original xy system, when we figure out what this intersection point is, in effect, we're going to create a new coordinate system, x bar, y bar, so that in the new coordinate system, the intersection point is the origin, 0, 0. And what happens is when we make this substitution, then it turns out these two constants will go away. We'll have different variables up there. We'll have x bars and y bars, but we'll have now a homogeneous coefficient problem. So that's the idea. Rather clever. Unfortunately, it's rather messy also. So let's dive into it. It's a tedious process, particularly if you go about checking yourself. Now, the standard one of the standard techniques to solving a system of equations is to find a way to eliminate one of the variables. But there are a lot of ways to solve a system of equations, linear system of equations. I'll do probably what is maybe the easiest and most popular. Let's suppose we want to eliminate y. So if I multiply the top equation by 7 and the bottom one by 2, see what happens here. I'll get 21x minus 14y plus 28 equals to 0. Second equation will be 4x plus 14y minus 2 equals to 0. And when we combine these equations together, the y's cancel. That was the purpose of choosing these numbers. So I don't know how rusty you are at doing these. I'm sure you've done these before somewhere in your past to get this far. Alright, so we get 25x plus 26 equals to 0. And solve for x. X would have to be negative 26 25ths. Alright, now to get y, I could take this fraction, plug it back in and solve for y. into either of these equations, or we could do the same elimination process. I think I'll do that. Let's try elimination on x instead of y. So with 3 and 2, I want to multiply this equation by 2, this one by, it'll have to be -3 to get opposite signs. So we'll have 6x minus 4y plus 8 equals to 0. Negative 6x minus 21y plus 3 equals to 0. When we add down, I've got minus 25y plus 11 equals to 0. And so solving for y, we'll get 11/25, won't we? There we go. So that's the idea, and it's not a coincidence that we have the same denominator, 25. That doesn't always happen when you have integer coefficients in a system of equations, but it usually happens. Okay, it's a pretty common thing to occur for all kinds of great reasons. Well, now what are we going to do with this? Let me erase some of this junk here. I'm going to be left with this part. All right, I'm going to take each of these, and I'm just going to go ahead and bring the constant over. So I have x plus 26/25 equals to 0, and y minus 11/25 equals to 0. Now remember, we said we wanted the new coordinate system, we wanted the intersection point to be the origin of the new coordinate system with x bar and y bar. So what I'm going to do is I'm going to say, alright, well, let's let this be x bar, we'll let that be y bar. And so when x is negative 26/25, then x bar is 0. Likewise here, when y is 11/25, y bar is equal to 0. So this sets up a key substitution that I'm interested in. And except, in order to substitute, I'm going to have to solve for x and y in terms of x bar and y bar, because I want to replace the x's and y's up here. So, a little more erasing.